All right, so let's get moving. So reminder quizzes are this week. Also a reminder, I'm getting emails from people with their regrade requests. Please do not email me your regrade requests. Bring them to the, we're up against this 2 gigabyte limit in our email. And anytime you guys email me something that you've copied, I immediately delete it because I'm always over my capacity. So print it out, bring it to the chemistry office, where I will leave it there I will leave them all there and let them pile up to the end of the week. And then at the end of the week or Monday morning, probably more likely, I'll go in and grab them and do the regrades. So you have to the end of the week, but again, bring them to the chem office, have the administrative assistants there put your regrade request forms into my mailbox. And at that point, you've sort of lost your chance. Okay, so today we're going to start returning back to reactions upon reactions upon reactions, but hopefully what I will largely try to convince you, again, as we try to do often, is that we're not necessarily learning anything entirely new, that a lot of the chemistry that we're seeing is sort of based upon what we've seen in the past. And today, what we're going to be focusing our attention on is sort of how we can functionalize benzene. And there's a couple different classes, sort of electrophilic aromatic substitution, nucleophilic aromatic substitution. Both of the stuff that we'll do is actually electrophilic aromatic substitution, meaning that we're treating the aromatic group to an electrophile. And what happens, as we'll see, right, is that we will, in essence, substitute our molecules with said electrophile. And obviously, as I sort of have written here, it's not necessarily it's not necessarily Balance's equation, so obviously the side problem would be plus.
Was it just a monitor?
It was just a monitor, yes. So if you could turn this so I can. Can it not project here? Or is that not?
Oh, yeah.
Yeah. Say that again? So we're going to get into that. I'm just sort of giving an overview. So what we're going to be really referring to here is electrophilic aromatic substitution, right? And so in essence, the byproduct in this process is hydrogen. And if you think about what we're doing here, right, we're really functionalizing. I guess I drew the resonance. I know that's sometimes confusing. I don't even think necessarily that I'm doing it. But if you think about really what's happening here, right, what we are doing is largely functionalizing electrophiles, right, where you leave behind a positive charge, right, and then sort of elimination takes place, where now we have our proton source, okay? And so the reason why I'm sort of showing you guys this in analogy to alkenes is we don't necessarily see that subsequent elimination in alkenes, but we certainly do see alkenes reacting as nucleophiles and reacting with electrophiles a lot, right? And so one of the classic examples of that would be, one of the earliest ones that we've learned, right, would be, for example, bromine. Right? So if we take this molecule and we treat it with bromine, right, which we will often draw as the bromonium, right? Sort of the bromonium ion, sort of bridge, right? And usually in our case, what we do is we take then with the bromide, we sort of add back in, right? And we add bromine across it, okay? Now, if we were to do this same reaction of bromine, right, across benzene, there's really two differences to the reaction we want to take into account, right? So this we all know, bromine reacts with that. It doesn't do the elimination. But if we take, I'll sort of introduce this. Okay, so that's chemistry that we all know. Okay, so let's go back to this. So benzene will also react with bromine, but there's a couple differences. And let's just start with what the product would be and why that product would be, and then we'll discuss why the reaction I'm going to show you might not work that well, right? So if I were to take this benzene and react it with bromine, and I'll just leave it there. Right? The product that we would get, instead of having the bromine add here, right, we might instead eliminate, right? And then our byproduct would be HBr. So 2 points to make about this. So the first part is, why do you think the bromine would not add 1, 2? Why would the bromine eliminate? Yeah?
Because of kinetics. It would be faster for it to just take over the hydrogen.
Well, why wouldn't that have happened with the alkene? Right? Because then we would have seen it with the alkene. Yeah?
You have the ring, and it's on sp2. It's not going to be able to form a bridge.
It could do the bromonium. Sure, you could definitely make a bromonium here. I could draw electrons that could show it. What's that?
This is stabilized on the slide up. That positive charge is stabilized by the ring.
Yeah, but if you had a dying system, it would have the same thing. Abraham, you had your hand up?
Would it prefer to stay as benzene because it's more stable?
Yes. Right? So benzene, we just spent all last class talking about how stable benzene is. So given the option of the bromine attacking here or re-aromatizing, right, we might get and understand, for example, that it would rather just do an elimination. Okay, so that's the first part. If you react this molecule with bromine, it'll go here. Except that if you took this molecule and treat it with bromine, it wouldn't go there. Okay? We need something else. Why might bromine not be strong enough to do this? We have to add something else if we can point to this. Yeah?
Do you add heat in order to push it?
Now, heat, well, we'll talk about it. You have to add a Lewis acid. So to actually get this to form, what you need is a Lewis acid. So FeBr3 is often shown. There's different versions. So the only way that you can actually get this electrophilic aromatic substitution to work is with a Lewis acid. Okay? That Lewis acid, right, as I'll show in the mechanism in a second, will actually make this more electrophilic. Why do you think bromine in its current form, just by itself, would not be strong enough to react with benzene normally? Well, I already know what Abraham's going to say, because he basically said it the last time. You're going to say it's stable because of aromaticity, and you'll be right. Is that what you're going to say?
I was going to say pKa.
No. Okay, so I should have. No. There's nothing to do with pKas. It has everything to do with stability of the benzene, right? Here, that's why I thought you were going to go there, Abraham, because you said benzene is stable, so the bromine will want to go. Instead of adding here, it will want to eliminate, right? Because it likes to be aromatic. By that same concept, this is already aromatic. So what has to happen in order to add across that bond? You have to break the aromaticity. Everybody see that? So there's a higher energy that's going to be needed, right, for you to break the aromaticity. So you need in most cases, sometimes, I just screw up what the guy just did here. All right. So bromine, right, is not going to be strong enough to add across this by itself. What we are doing is we are breaking aromaticity. That's higher up field and energy. than simply reacting with an alkene. And so the mechanism that I've shown here of the benzene attacking and one of the alkenes in the benzene attacking Br2 is not exactly accurate, because I just said it's not hot enough. And I'm going to show somewhat of an oversimplification here, but it's something that we can use to, I think, help make sense of a lot of things that we're going to see, right? And that is that when bromine reacts with FeBr3, iron is a good Lewis acid. It can, in fact, take on the bromine and coordinate to there. But usually what we often like to think about is a sort of an extreme example, right, where we have really a Br plus and an FeBr minus. It's not exactly like this. It's something sort of in between where where basically the bromine's giving up its electrons to this, so it's sort of taking on a positive charge in a way. Right, this is sort of taking on a negative charge, or maybe it's just a chelation type event where it's a delta positive here and a delta minus here. Again, it's somewhere in this ballpark, but I usually like to just think about it as a full-blown sort of positively charged Br, right, with the bromine kind of taking that. What that ultimately means is then from the deprotonation, to get the Br minus, though, you'll sort of have to dissociate that to regenerate that. So, okay. Okay, so this is how you brominate an aromatic group. Before I get into some of the other analogous versions to this, I would like to talk a little bit about some of the regiochemistry that you can get with electrophilic bromination, as well as the rates that one might get with some of this chemistry. Okay. All right, so I have a question for you guys. And I'll just start it here, and let's just think about this. If I ran the same reaction, but instead of doing the reaction on benzene, if I did it on, say, for example, anisole, right, methoxybenzene, right, I could in principle get 3 regioisomeric products, excluding dibromination. So we're just going to focus on monobromination. Right. What's going to happen is we can get as many as 3 products. Okay. Okay, so no, so if the 2 more that you're thinking is keep going up here and up here, I just flip it upside down, right? So if that one there is the same as if I flip this that way. It's symmetric. Do you see that? And same thing here. If I flip this over, that bromine would be over there. Yeah, so this position here would be identical to if I was up there. Okay. All right? Okay, so there's these 3 possibilities. The naming to these, we often use names to these. So this is what we consider ortho, meta, para. And this is nomenclature that's often used to describe the relationship between a couple different groups on an aromatic ring. If they are on adjacent carbons, they would be ortho. If they're one carbon apart, they're meta. And if they're on opposite sides, they're para. Okay, so the question is, we can make these three molecules in principle, which would be preferred? And the question that I had would be, and why, right? So let's talk about, even if we didn't know this, if we hadn't studied ahead, if we didn't know the selectivity of a reaction like this, we can try to reason it based upon what we do know, right? And so let's talk about that briefly. Right? So if we were going to react with this alkene here, let's talk about the intermediates to each of these. Okay, so if we're going to add ortho, right, after we react, right, that's going to be our intermediate. If we go meta, we will be there, right? So the next two will have to react with the other side. So this would be the meta. You see how when we added meta, say when we added ortho, right? Just like when we had bromine adding across double bond, right? The bromine ends up on one side, the carbocation ends up on the other. Here, the bromine ends up on one side of that double bond, the cation ends up on the other. Then we're just going to flip-flop these here. Bromine's going to end up on this carbon, the carbocation is going to end up here. Okay? Now let's evaluate these three possibilities. And let's start to ask ourselves, of these, which might be the most stable, and which ones might be less stable? Yeah?
I was originally going to say para because they're anti to each other. That's typically I'm thinking new projection style, that's stable. But
No, yeah, so this is a flat molecule. There is something to be said about separation. So anytime we're talking about chemistry and selectivity, there's really two, I think, ways that we can think about it, right? Sterics, right, and electronics. So those are really the two things that we consider. Sterics, students usually have a decent time thinking about. Electronics takes a little bit closer looking to get comfortable with. Both of these driving forces can dictate what takes place here, but overwhelmingly when we talk about this chemistry, we usually will start referring to electronics. So yeah.
but I would say the first answer is the most stable because it's secondary to that carbocation.
Okay, so that's this has a resonance form here, which basically would stabilize that, right? So you like that resonance form. So you like the fact that it's tertiary, has this resonance form, right, where that carbocation, basically now the molecule that we're drawing, right, doesn't have all its octets are full, right, here. We don't have any that doesn't have an octet full. Okay, so that's a good one. So that's one reason. How about these other two? Do we see any? They all have some resonance stabilization, right? Because they're all allylic cations. Do any others maybe look similarly good? do you guys think? First one's good. That looks good to me. What about these other two, though? That is good. Let's look a little closer. I want you to direct your attention to this one right here. Start thinking about the resonance forms, the additional resonance forms of that structure. Go ahead and start drawing it down. Don't say anything yet, but just start drawing it. I just give everybody a few seconds. Draw the resonance forms. Draw a resonance form of this. There's only one resonance form that we can draw here, right? Well, there's lots of resonance forms from it, but there's a first resonance form that we can draw, right? Where is it? Ronnie?
Push down the O.
Oh, you wanted to go right there. I was just gonna go one step first.
And this will place
Right? What's that?
this will eventually place a positive on an oxygen.
Yeah, so you can do the same thing you did over there. So the point is, the resonance form, right, that we saw over here, that you guys immediately picked up on, right? If you just push the electrons one place, you can get to a similar cation, right? So that positive charge can be on both of them, whether you react ortho or para. We can do the same thing here. If we push the electrons here, we're going to get delta positive here. Then we push them there, we're going to get delta positive there, right? So one of the things that we see in benzene systems, right, is that, yeah. Which one do you think?
I think it's a third
I'm gonna let that linger for a bit. Let's just discuss this really quickly. So this is, in this case, if you have a positive charge there, really that positive charge is going to be shared here, here, and here. If you have a positive charge here, it's sort of shared here and here. Likewise, that one is shared there and there. So both of them have the opposite resonance. So I'm getting a vote for the first one. I'm getting a few hands raised. Let's just, so we can all agree that this one's not. So now the question is it this one? Or is this one? Show of hands, how many people think it's this one? How many people think it's this one? I got more hands for that one. How many people think something else? Jan, what do you think? Jan suddenly thinks the second one. No, it's not the second one. Come on, Jan. No, it's definitely not this one. It turns out that it's can be both. You won't get selected. What's that? Well, let's think about it. So it's not. So okay. So let's describe this a little bit more because it's depending on the conditions. What do you think? Absent from, if you assume that those electronic effects are equal, which one's going to be the major? Why? So I'm hearing less steps to do it. This is going to be the constant question on the next example. Percentage. 50-0-50? No, it's not 50-0-50. You're pretty close. Why? You said 60-40. No, that's what Irina was saying. It's that can certainly help, right? So there is a proximity-induced effect where the positive charge that you would want would be a little bit closer. That may dictate to a certain extent, but there's something else that's fairly apparent, but you guys are probably overlooking. Yeah. Well, same thing here. Resonance forms are just, yeah.
That one you're sharing with a few carbons. Is
No, you guys are dancing around this, but it's like it's mathematical. It's just mathematical. What's the equivalent position of that one? If I had there or there, it's the same thing.
There's 2 spots for that.
So really, it's not this and this. This and this are equivalent, but there's an extra one of these, right? So this is the same chance as this, which is the same chance as this. Just turns out that there's 2 of those, right? So absent from any, so only stereoelectronic, and maybe it'll be not exactly that, because like some of you guys are saying, well, it's a little bit closer to the charge, and you'd probably be right? That would probably push it a little bit if it's electronically a little bit closer, but roughly it's probably going to be about 66-33. So if I told you that it was 60, if I told you there was more of this, that might be one thing that you said. If a couple people said, well, it's closer, so maybe it's easier to stabilize that positive charge, that's a reasonable answer as well. What if I told you it was this one? What if I told you it was that one? Why might you think, if I just told you I just made all that up, and in fact there's only 20% of this and 80% of this? How might we reason that? Yeah.
Think about it like in a chair structure.
Well, you can't be chairs with these, right? They're flat, they're planar. Yeah.
You might think about like the reaction condition. Like this looks like the one that.
You're getting closer. So if you think about, so the answer was sort of thermodynamics. I think you're getting there. So why would you think that this would be the thermodynamic?
Because it's more stable. This one.
Yeah, but why would this be more stable? It's a you're giving a circular argument. You're saying it's thermodynamic because it's more stable, right? It's a circular argument.
We're asking why is it thermodynamic?
Why? Yeah, why?
Because both groups are anti-neutral.
And why would that be good?
Because they're further away.
Okay, so what are you arguing? You're right. What are you arguing? I'm just trying to get you to define, to refine your answer a little bit more. So why would this might not be as good as this? Hindrance, steric hindrance, maybe. So sterics. I'm just trying to get you to refine your answer. You're on the right path. I just want that answer a little bit more refined. Yeah, so you might argue that maybe sterics. It wouldn't necessarily be thermodynamics. It could also be kinetic controlled, right? Because you'd be attacking at a carbon close to that. So that's another possibility as well. And it turns out that, you know, bromine's fairly small, so it's probably you're gonna get a bit more of the sort of electronic type answer. But if you have bigger electrophiles, as we'll get to in a minute, maybe you can dictate it a different way, okay? So anyway, so this is just the point that I wanted to make, is that for the sake of this course, when you're doing electrophilic aromatic substitution, both ortho and para, you will not get meta substitution. You will get ortho, you will get para. For the sake of this course, you can kind of assume that you can get either. In a synthesis problem, assume that you can get either. If I ask you a concept question, right, and that concept question starts to ask you to nitpick on ortho versus para, these are the types of things that I'd be looking for, right? Sterics, right? Maybe a stoichiometry-based thing that I'd be looking for there. So just trying to get beyond the ortho-para and look a little bit deeper. That's might be, if a concept question came up, that's kind of what I would be looking for. Yeah?
So it's 66-33.
I don't know. Yeah, but that's it's, I don't know the exact number, but I think you're more likely going to get a bit more of this than that, just because of the numbers. But I don't know. I think the numbers in your book, I think it's, I forget, but it's not exact. Again, because there's these other features that can crop up. Yeah, I don't see a percentage here. Yeah, so they have it for some other reactions. They have the percentage for nitration and some other things. They don't have it for the bromination. So, all right. Anyways, okay, so in general, now sort of I just wanted to introduce that, and that's going to be the case for any electrophilic aromatic substitution reaction that we see. It's going to be, well, I take that back. If let's no, I'm not done yet. Hold on. So I almost just went by without saying the important thing. Okay? It's not always going to be orthopara. It's going to be orthopara when you have a group that can help stabilize those positive charges that we just said. Right? So donor groups, right? Donor groups are what are going to stabilize. Okay? So if a donor group stabilizes ortho and para, right? What's going to end up, what do you think would be a reaction that might favor meta? Withdrawing group. What do you think an example of a withdrawing group would be? Withdrawing groups are tough because sometimes withdrawing groups will actually make the chemistry not work at all because now you've got an even, you're withdrawing and so the aromatic group becomes a weaker nucleophile. I tend not to worry about that too much in this class, but yeah.
Like fluorine or iodine?
Okay, now you get to a trickier in between one. We'll get to that one in a moment. Ketone, yeah. Let's say, for example, ketone. Is that what you were going to say, Ronnie?
No, but I was going to say maybe some change the solvent.
No, we're just talking about a group here. So let's make it a methyl ketone. Or, because of whatever, methyl ketone's fine. Okay, so we just switch this up to the methyl ketone. Methyl ketone might be the greatest because we know that bromine can brominate methyl ketones, but whatever. We'll just do this for the moment. Let's go through that same process that we went before. Just left this up here. Okay, so now we just found the same thing. I just redrew it ahead before there, but we swapped out the methoxy for a methyl ketone. Now we said that, yeah, that's where we're going, right? Second one. But explaining why this would be the case, why do you think that this resonance form would help explain this? In the past case, we had a donor group there that could help donate. Why might this group here not be great? How would we draw this? How would we visualize, if I asked you why this group was worse, right? How would you rationalize that? They all have an aromatic group somewhere, but what is it specifically about this one, Rami?
You can get two positives next to each other.
Yeah, we know that ketones have that delta positive there that we could actually reflect as a positive charge, right? So you're sort of putting two positive charges next to each other, which it really wouldn't like to have. And we could do the same thing here, right? Right, if we move that double bond there, we're now going to have that same resonance form that we showed before, right? And for the same reason, and you can push the electrons around like we did previously, you won't have that same problem necessarily here. Yeah?
I wasn't even thinking that. I was thinking tertiary benzoic versus secondary benzoic.
Well, this is what you have to be careful about, okay? Because I've gotten this answer in the past from people, right? Maybe even last semester, I'm trying to think of examples. But tertiary, secondary, primary, you might say that's good because it's tertiary. But it's not good.
Great.
It's not great. Why is this not a great tertiary carbocation? Because of what we just said. It's adjacent to an electron withdrawing group. You have a delta positive right next to another delta positive. So this is an instance where, again, it's not always primary is better than secondary versus the tertiary, right? Oftentimes we have to look beyond that. We have to look what the groups are there. Here we have an instance, right, where you have an electron withdrawing group, which, as Rami said, now you have positive charge next to another positive charge. It's not going to be very happy. It's the same reason why, for example, earlier, right, when we started talking about resonance forms of this, right? So we can go one way or the other, right? It's all right. I mean, there's an additional resonance form from the negative charge through there, right? But in addition, this is a primary carbocation, right? Which we don't like. And this is a secondary, which we like. But again, you have that sort of second positive charge next to it. So it's not a perfect analogy, again, because we do have that negative charge that also is stabilized to resonance. But this is another example where we've seen in these systems how delta positive, delta minus exists on these systems. Okay. All right. Okay. So that's one way that we can sort of view these. If you feel like you might be uncomfortable in scenarios like this because of things like what Abraham just brought up here in terms of tertiary carbocation, the other way that you can sometimes approach these problems is kind of doing what I did over here with these molecules. Sometimes that can be helpful as well, especially with something like this. So instead of just protonating the molecule right off the bat or brominating the molecule right off the bat, we can think about the electronics of this system. Right? Oops. And instead of actually brominating, you see what I'm doing here? So instead of brominating, I'm simply moving the electrons. So this would be A. This would be B. This would be C. Right? So if we think about the sort of the resonance of the aromatic system itself, which in a way can help reflect how the electronics of the system are, this is another way that you can sort of visualize that, right? And in this way, we're not only considering the carbocation, which we inevitably were having to consider when we started with the bromination. In this case, we can also consider kind of like what we did over there with the negative charge, right? This negative charge can't go up into that carbonyl. This negative charge can. So this might be another way that you can think about it. Either way that you think about it, it's fine. But you can, yeah, Aisha. That's kind of, yeah, that's what I'm getting to. And within that, kind of, then what we're saying here is in a system like this, right, if that's your delta minus, that's your delta plus, that's your delta minus, that's your delta minus, that's your delta plus, right, I'm just sort of going around the ring here, right, and where my delta minuses are, those are the more nucleophilic carbons. Does that make sense? So that's another way that you can think about it. Either way is fine. Either way is equally correct. It's just a way for you guys to be able to rationalize why the regioselectivity for halogenation is what it is. I think it's a bit easier sometimes to see when there's a donor group than it is when there's a withdrawing group, especially because of these things that just came up, like the tertiary. Hey, that's tertiary. Well, there's a ketone there. Well, maybe this can be another way that you can rationalize it where you don't have to make that jump. Okay? All right, how are we doing? Okay, so this is regioselectivity. You know, the book will discuss that sometimes if you have withdrawing groups, and this should make sense, right? If our benzene in electrophilic aromatic substitution, our benzene group is our nucleophile, right? Right? If the benzene is reacting with an electrophile, the benzene is the nucleophile, right? So the more electron-rich the system is, the better the nucleophile it's going to be, right? The more donors that a group has, the more nucleophilic it will behave, right? Conversely, the more withdrawing groups a system has, the less reactive it will be. And so I generally don't worry about like this too much, aside from this point that I want to make here. Because if you read the book, it will talk about how some reactions will never go with an electron withdrawing group, right? And I if you want to remember that, that's fine. I sort of give you guys a bit of wiggle room because if we gave something enough heat to the system, we could probably get it to go. But just, you know, just for the sake of rationalizing, and this is just a graphic depiction, just so you can start to think about it. Right? If you have an electron withdrawing group, it's going to be this is relative reactivity. Okay? So if you have a donor group, right, it's going to be more nucleophilic. If you have an electron withdrawing group, it's going to be less electron withdrawing. And I probably don't then have to tell you guys that the stronger, if it's got a really strong donor group, it's going to be an even better nucleophile. If it's got an even stronger electron withdrawing group, it's going to be an even stronger withdrawing group. So an example of, like I gave you guys methoxy, that's a really good donor group. A methyl group is also a good donor group, right? Because of that tertiary carbocation you have there. It's not quite as good as the methoxy, but so there's a relative effect, right, of what makes a good donor group, what makes a good withdrawing group. The one tricky thing in this, and so in general, if you have a withdrawing group, it's going to be meta. If you have a donor group, it's going to be orthopara. There's one slight caveat to that. Mark, were you going to say something? Huh? No, methyl group also behaves as a donor group.
I know, but like the methyl group is going to, if you move them over, it makes a negative charge, and the negative charge is bad when it has more groups next to it.
Well, you can make the argument. Well, so if you have a methyl group versus a methoxy group, that methyl group, now you go through the system. If you just switch out on the drawings that I had before, I'm not going to go through this, but if you switch out the methoxy from a methyl, right, you don't have that same resonance donor, but what you do have is you have that tertiary carbocation, right? So the methyl group does serve as a donor by allowing for the positive charge to be on a tertiary carbocation. That's not an electron withdrawing, position on it. So does that make sense? Got it. Okay, now the one caveat to this orthopara versus meta is halogens, okay? And so this is the one that you guys sort of may want to consider, right? Halogens, chlorine, bromine, fluorine, iodide, all these guys, they don't have that same back bonding or that same donor capabilities that a methoxy has. So they are actually electron withdrawing groups. This is one of the reasons why overhalogenation doesn't take place, right? If you brominate something once, brominating a second time is going to take more energy because you've added an electron withdrawing group to it. Does that make sense? Right? So once you've added an electron withdrawing group to it, it's sometimes difficult to then add the second. But it does go orthopara because you can still have the resonance from the halogen. Does that make sense? So we can still, I'll just show it with the ortho. That same resonance that we showed previously right? That same resonance that we had previously for the methoxy, you could also have for the halogen. Yeah. Fluorine's not doing it. Fluorine's like the most electron withdrawing. No. Fluorine is like the electronegative atom of electronegative atoms. Yeah, you're thinking of something. You're probably thinking of something else. But fluorine's. You may be thinking of, I don't know what you're thinking of, but I don't know, but maybe you're thinking about anion stabilization. That's where fluoride's a bit different than some of the others because it's small. But we're talking about withdrawing capabilities, and fluorine, in terms of having electron withdrawing capabilities, it's got the highest electronegativity, right? So that's it in terms of regiochemistry and the nature of what can be on there. Yeah, Rami.
We're going to deal with like reactivity of different numbered cyclic aromatic compounds. Like if you had like 10-membered ring, 15-membered.
Oh,
ring.
yeah, no.
Will those be generally more or less reactive?
I don't know. Probably depending on the system. Like naphthalene, something like naphthalene, right? Which would be I'm just guessing here, I'm speculating entirely, right? Like, that's naphthalene, right? And naphthalene is a 10-electron aromatic system, right? But I would bet that naphthalene would probably brominate faster than, I don't know this for a fact, but I would guess it would probably brominate a lot faster, simply because you can still maintain some aromaticity. You're breaking the 10-electron aromaticity, but then you're swapping over to a 6-electron aromaticity system. So. I'm guessing there, though. I don't know for sure. Okay.
With the aromaticity for naphthalene, would you end up with anti-aromatic molecule?
No, because it's not now in conjugation. If you've broken, right?
So now let me stay on the left side.
Exactly. Right. So you remember for an aromatic system to exist, you kind of have to have p orbitals on all of them. The moment that you functionalize one of those pi bonds, you've now turned that into an sp3 hybridized carbon. Okay, so there are a lot of reactions that benzene can do through electrophilic aromatic substitution. So we'll go through some of them. Okay, so in general, in order to do electrophilic aromatic substitution, you need a really strong electrophile. So as I did with the bromine, right? If you're gonna, and I should say that chlorine would do the same thing. Chlorine and bromine, you just, in that case, I think it's FeCl3 rather than FeBr3, right? Or AlCl3. FeCl3 is what it says in your book. And actually, the book points out something else that I should mention right now because I just sort of said this. Rami was just asking about nucleophilicity of different groups. I showed anisole there, right? And we treated it with FeBr3, and it's probably a good habit to just get into to just have it react with FeBr3. But what if I told you that while benzene required FeBr3, that anisole, that methoxy group donor, didn't? That makes sense to a certain extent. So it turns out that you don't always need FeBr3. If you have a really, really strong and a really electronically rich aromatic system, like furan will do this really readily. Like if you take furan will actually brominate, even though it's aromatic. You just treat it with Br2, and it will brominate. You don't need FeBr3 for that. And I showed earlier the methoxy donor group, which is a really, really strong donor group. And so if you have a really strong donor group, you don't necessarily need the FeBr3. But I would just use it. I would just get in the habit of using it anyway. But that's just in case you read the book and it talks about certain aromatic systems don't need FeBr3. Those are groups that have really strong donor groups. So that goes back to what we were just saying about relative reactivity. So the further we were to the reactive side, you may get away with not needing to use the FeBr3. But in general, we'll need that. Okay, so we can add chlorine, we can add fluorine. One of the other reactions that you can do is a nitration. And what you do in the nitration is you take nitric acid and sulfuric acid, and you treat it with the aromatic molecule. And what you actually generate in this chemistry is you actually will add a nitro group. Okay, so from nitric acid, we're going to generate an NO2. So let's think about how this might happen. I just told you guys earlier, right, that for electrophilic aromatic substitution, with some exceptions where you have a lot of donor groups, generally you're sort of generating a cationic electrophilic species. That's why we think about the FeBr3 coordinating to the bromine and generating Br+, right? It's just a way to sort of rationalize this and think about this. Well, it turns out that nitric acid and sulfuric acid will react together to generate a very, very electrophilic source of NO2. And so if we think about what that electrophilic source, first of all, do you guys know what a nitro group looks like? Yeah, it's sometimes people struggle to draw nitro groups. They'll see NO2 and they'll struggle to draw it because it's one of these rare examples of a group that's actually zwitterionic. And so we might not want to draw it that way. But when you have a nitro group, it's got negative and positive charges next to each other, right? So, so nitro group is one of these few examples of a neutral group that is actually zwitterionic. It's kind of like an ylid, right? The ylid that we had, right? So, so that's a nitro group. And if you think about what the electrophilic source that would put that nitro group there would be, right? It's actually this group right here, okay? Sometimes you'll hear things called HONO as well, and we'll talk about HONO a little bit. But usually I just sort of think about it this way, right? That's if you add into there, right? Once we add in, right, we'll get to this molecule here. And in fact, you've got sulfuric acid in there, so technically that could be protonated as well, but let's just stick with this. So if we think about nitric acid, nitric acid looks like that. So again, nitric acid is zwitterionic in nature. And the question that I have for you guys is, and this is kind of a mechanism question. How might we get to something like that? Yeah.
Eliminate the oxygen and sulfuric acid from the OH.
Yeah.
The lone pairs from the oxygen makes a double bond. So
Yes. Okay, so what'll happen, right, is there's a couple different ways that you can think about this, right? The most electrophilic, or sort of the most nucleophilic, obviously this oxygen can be shared on those through resonance, but you can often initially protonate at that carbon, right? Right, so that's one way that we can think about this. What I usually do, because it just, I think, simplifies the mechanism, even though it might not be entirely accurate, is to get to a species that looks like this, right, you are eventually going to need to lose what? You're going to lose water, right? You can't lose water at this point, you'd lose a hydrate, right? So you'd actually have to protonate this again, right? And this is why I don't like this that much.
Where's it protonated from?
Huh? Yeah. So for more sulfuric acid. So you've got a lot of sulfuric acid. And I'll explain why I don't usually go through this mechanism, because it makes me feel uncomfortable. But this will explain the sort of the HONO that you'll often see in the book as the reactive intermediate, which is probably more likely. But here we have a positive charge next to a positive charge. And you're not going to avoid that if you're going to lose water, right? Right? What's that? And the oxygen also has a positive charge. Right? So now we have a 2+ species. I don't like this that much at all. Right? So usually when I draw this mechanism, what I will do is I'll start here. Right? I'll usually start here. Even though kinetically you might want to go over this place, I usually like to protonate this first.
But that doesn't make sense, really.
Just bear with me.
It's an O minus.
Because it's a global equilibrium. We can think about it that way, Rami. Rami, you can think about it as equilibrium, right? it'll first want to deprotonate there, but eventually that proton will find its way over here. And once it finds its way over there, we can lose water, right?
Doesn't make sense. Just by just simplifying it, still doesn't make sense.
Yeah, it's not the most comfortable of mechanisms. I'll admit that.
They're all additive to the same thing.
Right. Okay. And so we'll lose water and we'll effectively get to this intermediate. So this is ultimately your electrophilic source. Okay. Now if you use this as your electrophile, right, I'm sure you guys could carry that through. This will attack. You'll end up with your nitro group and then you'll do your elimination. Okay. But again, the critical point in this, right, is generating the electrophilic source, which is this. Okay.
Isn't NO2 a gas?
What's that?
Is NO2 a gas? I'm thinking something else.
Two. So there's this. Oh, this is never mind. That's not. Okay, so NO2. Like you're thinking of like nitrous. Yeah, I'm trying to think. I'm not thinking clearly right now. But anyway, so this is going to be your electrophile. Okay. And again, then you'll react with benzene. Okay. All right. So that's nitration. So get to this species. I think I actually just started confusing a few other reactions. But anyways, just that's fine. You get to this species. That becomes your electrophile. It attacks. You're then gonna end up with a nitrogen. All right, so another thing that we can do is we want to make sulfonic acids. In this case, it's probably a lot easier, right? I'm sure that you guys could probably do a mechanism for this. Right, we've got SO3. What is our electrophilic source for the SO3 going to be? For SO3H going to be? If we backtrack, right? If we backtrack what that cationic electrophile is going to be, right? It's going to be protonated SO3, right? We attack here, kick those electrons up, and we'll get to our sulfonic acid. Does that make sense? So it should be fairly straightforward here. We got SO3? Yeah.
You missed an arrow. Is this supposed to be an arrow or a double bond?
Where? This was an equal sign. That's what you're talking about.
Yeah.
Is that?
I like you meant to draw an arrow.
No, that was just equal. Yeah, I guess I could have done like that or something, but it's not really a retron. It's just trying to say this would come from that. So I guess it's kind of a retron. So anyway, so if that's what we want to get to, it's pretty easy, right? We take SO3. Protonate. Right? And that becomes our electrophile. Benzene reacts with that. Do the elimination as we did before, and you'll get there. Yeah.
I would think that sulfur at these higher oxidation states would be very electron rich. Meaning because it's broken, it's octet. It's got 12 electrons attached to it. So wouldn't that mean that the sulfur is electron rich? So all that make it a good electrophile?
Electron poor, you mean?
No, electron rich because I mean it's. I mean, if it would just have its octet.
It's you're talking about oxidation states. So it's sulfur. Again, remember that when we're talking about sulfur, it's down row.
Right, I know it can do that, but the question is, wouldn't that make it more more electron rich than say if it had its if it kept the octet?
Let's talk later. Because if anything, it would be a more electron poor, right? Because we're pulling electrons away from it.
Oh, okay.
Now, what you're saying is probably depending on the nature of the groups. So maybe in some instances, if you have more donor groups, then that would be, in this case, you've got 2 electron withdrawing groups. So. All right, so what have we put on this guy? We put on halogens, we put a nitro group on there, we put an SO2H, right? What we haven't discussed yet is, this is organic chemistry, and organic chemistry making carbon-carbon bonds. So the last set of reactions are how to make carbon-carbon bonds. And so there's a series of reactions that we can use to ultimately make, let's just say, R group. Let's start with maybe, yeah, so the 2, I'm just trying to think. We'll start with, did you say acetylene? Did somebody say acetylene? Yeah, I think acetylene is probably a good one, and then we'll go to the Friedel-Crafts stuff. So let's start with alkyne. So one of the best ways, and one of the ways that you guys know, for example, that you can make carbocations, right, is, for example, if our electrophile, right, is going to be a carbon-based electrophile, then in the same way, we'd like to try to make a positively charged carbon atom. And one of the ways that we know how to do that is with alkenes, right? If we take an alkene, and we have it on the sulfuric acid, in this case, it's good to try to predict what we would make, right? So if we have sulfuric acid, we have an alkene, we have that benzene, can we predict perhaps what this product would be? So what do you think the first step? Again, we want to make a strong electrophile to react with the aromatic group. So the sulfuric acid isn't going to react directly with the benzene. It's going to react with the alkyl, right? Okay. Now that we have our carbocation, what's going to happen? Something's going to attack. Something being benzene. And then we can put that group on there, maybe by the OSO3H that we had from earlier. Maybe that's going to come in and protonate, right? And do the elimination, and we'll get our tert butyl group there. Okay? Okay, so okay. All right, so that's that. Okay, how else can we generate? There's one other way that we know to generate carbocations. Yeah. Grignards? You think Grignard? Grignards, no, that's not how we make carbocations. I guess, all right, it's sort of, it's an earlier reaction, right? We can do dehydrations, right? Well, there's a lot of ways that we can make carbocations, but another way that we could potentially do this, that the book discusses, is with alcohol sulfuric acid, right? Depending upon what that alcohol is, you can stabilize the carbocation, right? Now, right, I'll just, for the sake of time, we're going to lose water. We get our plus, R reacts, right, and then you do your elimination. So we know that we can generate carbocations from alkenes and acids. We know that we can generate carbocations from alcohols and acids. Okay. All right. So these will work sometimes, but these aren't the standard way that people usually think about making carbon-carbon bonds. from aromatic systems. The sort of classic ways, and the way that you guys should familiarize yourself, probably more so than anything at this point, is Friedel-Crafts alkylation and Friedel-Crafts acylation. Acylation or alkylation. Okay. Friedel-Crafts acylation, Friedel-Crafts alkylation are going to be very synonymous to what we saw with, for example, bromine, right? So in the case of bromine, activating bromine with FeVr3, activating chlorine, for example, with aluminum trichloride or whatever. Friedel-Crafts chemistry is our sort of halogen-based method. So we can make carbocations from alcohols, we can make carbocations from alkenes. We can also make carbocations from halogens, right? Like if we think about sp3, if we think about SN1 chemistry, right, our first leaving group is often the halogen. But what we need to do in this chemistry is in fact force the leaving group to leave. Again, you could use a number of different things. The classic example the book uses is aluminum trichloride, which is again a really good Lewis acid. What do you guys think happens here based on everything that we've been saying?
Wait, do the two halogens have to match?
Huh?
Do the halogens have to match?
Sometimes people do, because otherwise you may get crossover, but it shouldn't be a big deal. But yeah, so the point is Lewis acid, AlCl3 is plastic with some alkyl halide.
So you could be R plus.
Yeah, exactly. So the same thing with what we saw with FeVr3, right? And that's that Rx right, that we'll get that R plus. And so again, given the time, you guys could probably complete that. Yeah.
How does that X link? Does it leave on its own, or
So this is what we were saying earlier. This is a good Lewis acid, right? So what's happening is you get coordination to the AlCl3, and this is kind of what we were saying at the very beginning of class, right? That's what we said at the beginning. Is that it's probably coordinating and making it a better leaving group. So we're kind of drawing an extreme example to stay consistent with this theme of cationic electrophiles. Again, is it really a cationic electrophile? Most cases, probably not. One of the cases that I became personally aware of recently, and so this obviously, if you go through it, given the time, I just want to spend a little bit of time talking about making one other comment. Because this is something I didn't really truly appreciate until recently about the importance of this carbocation formation. I'm sure you guys could get there. But let me talk about alkylation would be if that R group was an alkyl group. Acylation would be if it's an acyl group. So specifically, we're talking about usually acyl chlorides. This is chemistry that works actually really well, in large part because the formation of the cation is okay. So and I noticed this recently with some chemistry that we were actually doing on an analogous system, very Friedel-Crafts-like. The ability to form the carbocation is kind of important here. And when we extract the chloride, right, whether it's through the AL3 mechanism that we had previously, what you're going to get here is a system that might not look the greatest in the world. Right? So you can draw it as this sort of cation and carbon. Usually people draw it as the other resonance form, though, right? Where you can actually donate down Right, so people often show this sort of triple bond to the oxygen, right, which just simply allows us to have full octets across the board. Right, this becomes our electrophile. We add in, yeah.
Is there any way for this to use this in like inorganic chemistry? It's a very similar mechanism. You have built bond over there.
Yeah, I mean, yeah, we can talk about it later. I mean, what you're asking is, can we trap out these electrophiles with other nucleophiles? And the answer would be, in a lot of cases, yeah, probably. All right. So, anyways, I'm gonna call that a day. So there's just a couple more reactions that we've got to cover next week. Then next class. Then what I will do is we'll talk about some more synthesis. So we'll spend some time doing synthesis of aromatic chemistry, in part because sometimes when we're considering making functionalized aromatic groups, you have to sort of consider donor withdrawing groups because then regioselectivity comes involved. So that's what we'll deal with next class.